Good day, everyone. Welcome to our standard and normal distribution and the z-table lesson. In this video, we will be discussing our second topic, and that is the standard normal distribution. In our previous lesson or topic, we had discussed the normal curve. Now we learned how to graph a given value into a normal curve that is using the Gaussian function. Here in our topic, we will discuss how to convert these values into what we call a z-value, okay, or the standard normal distribution. We will be discussing how to normalize a value. Okay, we'll go to our second topic, and that is standard normal distribution, or what we call standardizing values. As you can see here, this is our normal curve, right? And this is still the look of a standard normal curve. We can see here the percentage, a different percentage, and here are the what we call our z-score, and we also have our sigma or our standard deviations, and our cumulative percentage. Now let's start first with um, analyzing the figure here, this curve. Now we know that based on the mean, okay, if this is our mean, now the left side is symmetric to the other side. And if we recall our properties of a normal curve, now the total area is the total area is equal to 1, which means half of which is zero point 0.5, the other half is zero point 0.5. Now here are the distributions in terms of percentage. Now from 0 to negative zero point 0.5, which means now we will use the mean as our reference. Now we have to take note that using z-score, our mean is equivalent to 0. Okay, when using z-score now, we know that this is again our mean, and in the normal curve, we have different values here. If, say, for example, our mean is 25, so this might be 20. No, this side might be 20. Okay, this might be 15. It might be 10, 5, and so on. And you can have here 25, 30, and so on. But again, you just have to take note that when converting our values into a standard normal distribution, our mean will become our reference point. We won't use anymore the Cartesian plane. If you recall, the Cartesian plane that we use, the horizontal axis will be our x, and the vertical axis will be our f of x. In the standard normal distribution, our reference will be this middle here, our mean, and that will be our 0. To the left of the mean would be negative values. To the right of the mean would be our positive values. Okay, as you can see in the image, you will see there are different z-scores, no, and the cumulative percentage. So you have here a negative 0.5 z, no, a z-value, which is negative 0.5, negative 1, and so on. Okay, we can also see here that this value here is negative 1 sigma away from our mean. No? Then this one is positive. No, this one is positive 2 sigma away from the mean. So as I have told you earlier, half of which or half of this curve is 50% of the total area. So which means this portion here is 0.1. So you can see there the cumulative percentage. Then you have the 1%, 2%, 15.9, 30, so on 99.9, and so on. So this means as we increase the value of our z-score, Okay, the cumulative percentage also increases. Now take note that cumulative percentage are our we can say as our probability and also as our area. Now, the area of the curve again is equal to 1, so this can be equivalent to the probability of certain conditions to occur. And later on, again, these percentage will be our probabilities, and that will be discussed in our next topic, topic after this one. So here how we, as what I have said earlier, here is how we standardize a value. So you have a normal distribution, you have the mean at the center, okay, and when we standardize this becomes 0. The mean will become 0, and all of the values to the left of the mean are negative values, and all of the values to the right of the mean are positive values. So in a normal random variable, or a normal random variable is standardized by expressing its values as a number of standard deviations it lies to the left or right of its mean. So meaning, if we will standardize these values, now this 950, 970, 990, in standardizing these values, we are actually calculating how far away are these from our mean. Okay, this is the number of how many standard deviations are these values away from the mean. Will it be the we know that based on here, these one are to the left of our mean, these one are to the left of our mean, and this one are to the right. And to the left of the mean, when standardized, will have negative values, and to the right of the mean, when standardized, will have positive values. And again, that the total area is equal to 1. This is how we convert. Now, if you might ask, how do we convert this value into a standard normal value, or what we say, the number of standard deviations away from the mean? So we will use this formula. Z is equal to our value minus our mean divided by our sigma, which means we have to calculate first these two before we can convert it or before we can standardize the value. So here are some conditions. When x is less than the mean, so the value is negative. So when x is greater than the mean, so the value of z is positive. And when x is equal to the mean, the population mean, then our z is equal to 0. Okay, let's take this example. A survey of daily travel time has these results in minutes. So you have 26, 33, 65 minutes, 28, 34, 55, 25, 44, 50, 36, 26, 37, 43, 62, 35, 38, 45, 32, 28, and 34. And our task here is to convert these values to its equivalent z scores or standard scores. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So we have 20 values and convert them into z-scores. So using our formula for z, and that is equal to x minus mu divided by sigma, we can convert each of these values into their equivalent z-scores. You have here, but before that, we have to calculate first our mean and standard deviation. So I will leave to you the calculations of the mean, but I have here now the answers. So again, the mean is equal to the summation of all the values, of all your x's divided by n, or the number of the x's. And that is equal to 38.8. So kindly check if you will arrive with the same answer in your calculation. Next, calculate the sigma or the standard deviation. So I have already calculated them using our formula, the summation of the square of the difference of x and u all over n, and that is 11.4. So we now have 38.8 as our mu and 11.4 as our sigma. Then using our formula for z, please remember this, that is x minus mu divided by sigma. So say for example, we have, let's just um, say x, no, for x is equal to 26, subtract it by our mean, that's 38.8, and divide it by 11.4. Now, since our x here is less than the mu, or our mean, population mean, then we'll expect that we'll get a negative value. So what do you think is the answer to this one? So there should be a negative value. Do these to all the remaining values. So you have 33 minus 38.8 divided by 11.4. So what's your z? Then you will have another. So you have 65, 38.8, divide them by 11.4. So you'll get another z. So again, all of these will be converted into their equivalent z values. Now I have already calculated these, and these are the result. You have um, using z is equal to x minus mu all over sigma. So we have here. mm, okay, before that, I have shown first. Okay, this graph is not yet the with respect to the z functions. Now I have just shown here that these values here, when converted or used, when converted to their density equivalent using the Gaussian function, this looks like still a normal curve. Yeah, if we extend this one, or if we follow these points and extend them, we can expect that this would be the equivalent graph. Okay. Okay, we have proved earlier that this really forms a normal curve or a bell curve, right? So though this is not transforming the values into their density equivalent is not a say required when standardizing values. However, if in a problem you are required to do that, then you have to do so. But ideally, when you standardize a value, you don't need to use Gaussian function. I'm just showing you so that you can you'll be able to see now that this really looks these points here are actually found in the normal curve. This really form these curves, these points really form a normal curve. Now let's go back to calculating the z's. Okay, again our mean is 38.8. Our standard deviation is 11.4. So our z equivalent of 26 is negative 1.222807. Now that's negative, so our mean here is our reference, which is 0. So which means this first z here, 26, is approximately in this point. So if we extend this line, so our z is here. Okay, this is one. Now if we compare it with our normal curve earlier, when we normalize the curve, so that point should be here, and that's negative 1 point, let's just say 1.12, approximately 1.12. Okay, next. So when x is equal to 33, its equivalent z is negative 0.508. So approximately here. This will be our second z. Our third z is x is 65, so the third z is 2.29 or approximately 2.30. So maybe here, somewhere here. So that's our third z. So just to continue this one, so just continue converting them. So we'll have negative 9.47 for when x is equal to 28, negative 0.421 when x is equal to 34. So these are, after calculating, so these are the equivalent z score of the values. Okay, there are 20 um, values there converted. So that's how we convert um, a value into its equivalent z-score. Now, one application of this one is this problem. So say, for example, a professor, um, he is Professor Willoughby. So I think that's how you pronounce this one. Professor Willoughby is marking a test. Here are the students. There's students' results. There should be an apostrophe after S. Here are the students' results out of 60 points. So the students only got 20, 15, 26, 32, 18, 28, 35, 14, 26, 22, and 17 respectively. As you can see here, um, only one got more than 30 out of 60 points. And if we check, most of them will fail the test. Okay, now Professor Willebo analyzed this and he thought that the test must have been really hard. So he decides to standardize all the scores and decided that he will only fail those students who are one standard deviation below the mean. So meaning when we say one standard deviation, that will be on, if we check our graph, okay, that will be here. No, below 1, -1 standard deviation from the mean, so the students will fail. Okay, then the question will be how many of them will fail? So what should we do to solve this one? The first thing is, again, calculate the mean. After calculating the mean, so remember this, no, when standardizing, these values should be present, the mean and the standard deviation. Then after, we can then convert them into their equivalent z-scores. Each of x now will have an equivalent z-score. So if this is x sub 1, you'll have to calculate for z sub 1, x sub 2 to c sub 2, and so on. Now I have here the finished calculation. So all you have to do is to use your calculators, solve them, and check if you'll get the same answer. So the mean for this data is 23, and the standard deviation is 6.63325. After converting them, so using our formula, z is equal to x minus mu all over sigma, I can get an equivalent z-score. So for 20, that is negative 0.45227 approximately. For 15, when x is equal to 15, that's negative 1.20605, and so on. Now the question again is, how many students do you think have failed? Now we cannot or you cannot answer this question unless you have converted them into a z-score. Now, checking at our z-score, we will look for students which have below -1 z-score. So we'll have here, yeah, negative 1.2. So the student would fail. And positive, okay, we have another below -1 standard deviation. So which means there are only two students who will fail. Now there are only two students who got below one standard deviation below from the mean or below the mean, so which means those students who scored 15 and 14 will be the students who will fail the test. Okay, so the conclusion here is students who got 15 and 14 scores respectively will fail the test. So that is how we convert a value into z-score. So we have only seen here one of the applications or one of the uses of z-scores, using z-scores. And I would like to thank you for watching the video, and we'll be in the next video, we'll be discussing our last topic for this lesson, and that is standardizing or the standardized normal distribution using z table. Thank you.